Second. Perfect. Thank you for the reminder. So this has started last year, and essentially what happened is different sections in Europe got together and said, okay, can we start a series where we can share a little more about geothermal energy, about the synergies between geothermal and oil and gas? And this is exactly what has happened. So what we've tried to do is we've tried to tackle topics that are interesting in terms of the technical side, the economic side, and a little bit of understanding the whole concept of what's going on. I'm sure you've been hearing quite often recently that this is the geothermal decade. It sure is true that we hear a lot more about it than we did in the past, at least in the oil and gas. One thing I would like to make clear to all the people that are in geothermal for a while is uh, we know that geothermal has been around for a while. It's not like it just popped up 2, 3 years ago. So I think it's very important to give the credit to those that have been involved and have been developing this technology across the world. Um, Without further ado, I would like to introduce to you our speaker today. So Dr. Hamid Soros, he's a renowned geomechanics expert and the CEO of Tavera. He brings over 25 years of experience in subsurface engineering for oil, gas, geothermal, and carbon storage. So quite diverse. He's formerly with Dong Energy, Shell, Weatherford, Synergy, GMI, and Cyro. His focus lies in developing advanced technologies for sustainable geothermal energy carbon storage projects. With degrees in mining engineering, rock mechanics, and a PhD in petroleum engineering from Curtin University, Dr. Soros has authored numerous papers and served as an SP Distinguished Lecturer in 2012, 2017, and 2020. So I think we have just the perfect person here today with us. I'd like to thank Dr. Soros for being here today. I'll pass it on to you. At the end of the talk, we will be addressing the questions, so feel free to put them in the chat box, and then I will be addressing them to Dr. Soros and try to cover all of them if we can until the end of the session. Enjoy the session. Thank you for being here today.
Okay, thank you, Gabriel, for the introduction. Hello, ladies and gentlemen. First of all, I'm really pleased and honored to have this opportunity to present to such an esteemed audiences and several, SP sections. So if you don't mind, actually, I would like to turn off my camera to make sure that my bandwidth basically doesn't create any problem. My objective of this presentation is basically to introduce geomechanics and all the values that it brings to the geothermal industry, review some of the learnings from oil and gas. What are the overlaps that we have with oil and gas, and what we need to change, what mistakes we have been doing in oil and gas that we are not allowed to repeat when we are dealing with geothermal. And a little bit about future trends. So I think I already went through the agenda. My introduction would be basically a quick introduction to geomechanics and geothermal, and I will include a few quick slides on our company as well, just to make sure that you understand whom you're talking to. And then at the end, I'm ready to answer any questions that you might have. So a little bit about our company. Tavera, our company is an award-winning technology and consulting company established in 2014. And we are working on subsurface solutions for carbon storage, geothermal, and subsurface energy storage. We define our mission to basically transfer and apply learnings from oil and gas industry, those 160 years of now operations, to help accelerating clean energy movement. Our specific goal is to develop solutions and technologies that lower the cost of geothermal and carbon storage projects. Since 2018, we have received more than $6 million US in funding from US government and some from industry. And using these grants, we have been able to develop 9 unique technologies. A few of them already for market, and the rest is still under development. Our core capabilities, geomechanics has been historically always the core of our business, and all of our other capabilities center around it to kind of complete our geomechanics service chain. In the last 10 years, we have been able to develop, integrated technology workflows to basically go from geology all the way to geomechanics and different, engineering applications such as well design, hydraulic fracturing design, microseismic analysis, reservoir performance prediction, and subsurface monitoring and visualization. Almost all our integrated workflows to some extent involve new technologies and state-of-the-art artificial intelligence. And this is a glimpse of our projects. We have a long track record of successful geomechanics and geothermal projects internationally. Heavily, right now we are heavily oriented toward geothermal, although we have keep an eye on basically carbon storage, and it's still a little bit supporting oil and gas clients as well. With that said, moving to geothermal, I think all of you are kind of geothermal lovers or have some interest in geothermal. No need to basically talk about benefit of geothermal energy, but quickly reviewing some of the advantages of geothermal over any other renewable sources. The potential of geothermal energy is more than energy that can be provided by global oil and gas. So that's how huge this potential is. Geothermal, as you know, is renewable, is stable, with minimal carbon footprint. So it's very, very attractive with respect to environmental, and carbon emission aspects of the industry. Produce electricity consistently without regards to weather, right? It's not like solar and wind, which is heavily dependent on the weather. Unfortunately, growth in the US has been quite flat the last 2 decades. Solar and wind kind of, surpassed geothermal significantly, and the main reason for that is cost of geothermal development, right? Upfront cost is typically quite high, and the return on investment is quite slow. What's interesting is that majority of the cost, more than 50% of the cost of development, is related to drilling. And according to the World Bank, 22% of the geothermal projects that failed were because of the during drilling stage. Unfortunately, as of today, only 1% of global power coming from geothermal. And I think geothermal community, including all of you guys being interested in it, we should work really hard to basically increase this percentage to a more significant portion of the energy market. So what we are looking for. So to have a geothermal reservoir and being able to harvest heat from subsurface, there are 3 main parameters that we look at: heat flow, permeability, and thermal conductivity, right? Regardless what geothermal extraction technology we use, either it is advanced technologies or enhanced geothermal system or conventional, these are the 3 most important parameters that define if a geothermal project is successful or not. So the interesting thing is that all these parameters are heavily dependent on geomechanical characteristics of subsurface. The in situ stresses, the mechanical properties, faults and fracture system, how they are basically oriented toward a stress field. So geomechanics becomes a very important topic. Geomechanics is important for oil and gas, but moving toward geothermal, it becomes even more pronounced, right? So with that said, I start with a quick introduction, basically definition of geomechanics, what geomechanics is, for people who basically don't know geomechanics well. So geomechanics and rock mechanics, basically they are the same thing. I see some people in the oil and gas industry try to differentiate between these two, but honestly, they are the same thing. It's just different terminology that some companies use rock mechanics, some geomechanics, right? So geomechanics is the theoretical and applied science of mechanical behavior of rocks in the force field of their physical environment. So basically we have rock formations, right, under specific, environmental condition. There are stresses acting on them. There are pore pressure, basically fluid that has saturated those rocks. Temperature is around rocks, right? So the role of geomechanics or rock mechanics is to be able to help us predict the reaction of rock formation to all these, any changes to their physical environment. We drill a well, we produce oil and gas, we produce heat, we inject CO2 fluid. What is the reaction of these formations to these operations, and what are the risks associated with these basically reactions, right? So it's critical to know these things before we start touching a field. So geomechanics is applicable to civil engineering when we look at the foundation of large structures, in tunneling, in mining, and in oil and gas. So geomechanics has longer history in basically in mining industry and civil than oil and gas. In oil and gas, I would say, I mean, at least from the 70s, we have been to some extent applying geomechanics to better drill, to better basically frag the formations, and being able to improve productivity of oil and gas. So what is a geomechanical model that we need to be able to predict subsurface rock behavior, right, or reactions to the operations? A geomechanical model consists of 6 main components, right? That if we determine and calculate, we can claim that we have a geomechanical model. So these parameters are basically the in situ stresses, right? 3 principal stresses that in most cases in deep projects are, one of them is vertical and 2 of them are horizontal. We call them vertical stress or overburden stress, and minimum horizontal stress and maximum horizontal stress, right? The third parameter is pore pressure. So almost all the rocks in subsurface below the water level are saturated with either water or gas or oil, some sort of fluid, right? And this fluid is under pressure. So we need to know what is the pressure, basically fluid pressure inside the formations. And then we have one component called rock mechanical properties, which consists of several rock properties, including Young's modulus, Poisson's ratio, UCS, friction angle, and cohesion of the rock. These are the main rock properties. I typically, put them under one flag called rock property. And then the stress field has an orientation. So that is the 6th component. So on top of these main components, we have geological features like fractures, faults, formation tops that we need to basically include into the model to be able to predict their behavior. If we develop this model for along a well, we call it 1D geomechanical model. If we expand it to a 3D space like an oil field or geothermal field, it is 3D. And if it is coupled with reservoir, and we can look at the basically timely changes of the subsurface, we call it 4D geomechanical model, right? So the information that goes into a geomechanical model consists of geology information, as I mentioned, geophysics, geophysical information, petrophysical information, and informations from engineering side, reservoir engineering, like previous observations and experiences with drilling, with production. And integration of all this data basically allow us to have a geomechanical model, right? So this geomechanical model can be applied to shallow projects in mining and civil engineering, and it can be applied to deep projects like oil and gas, geothermal, and carbon storage and energy storage. Okay, so now let's move to geomechanics of geothermal. Just focus on some of the values that geomechanics bring to geothermal to make geothermal projects safer and economically more viable or more profitable. I would like to start with risk of wellbore stability. So wellbore stability issues are typically killers during drilling, right? If we cannot really deal with these instability issues that are coming from geomechanical lack of geomechanical understanding, they typically create a lot of non-productive time. From the importance point of view, drilling, I mean, going back to my comment about drilling being the largest cost component of the geothermal project, is very important to be able to actually reduce this cost, right, as much as we can. So non-productive time is very important here. Is less tolerable in geothermal than oil and gas. And the reason is that oil and gas projects are very profitable. The profit margin is quite large. We don't have that beauty in geothermal projects. So we really cannot tolerate, wasting a lot of time, right? And capital during drilling. So it's better to spend some money upfront and develop good geomechanical and wellbore stability models to be able to minimize, the time wasted during drilling, which is going to be 10, 20 times more expensive than, or even more expensive than data acquisition for geomechanics. So looking at closed loop geothermal systems, they require complex drilling program, right? We are creating a network of well bores underground to create a radiator to be able to harvest the heat from the formation. So drilling this well is really difficult. Bunch of horizontal, vertical, deviated wells that needs to get connected to each other and create that basically network. Without geomechanics, it's impossible to basically do those type of drilling. Wellbore breakouts is actually a problem that is valid to shale gas development as well, as many of you may know. I mean, breakouts basically create tortuosity around the wellbore. If you don't have a nicely shaped, basically circular shape for the well, typically hydraulic fracturing becomes a challenge, right? And we need more basically pressure to overcome the tortuosity around the wellbore. So it's very important to make sure that we don't develop breakouts specifically in the reservoir when we want to do develop enhanced geothermal systems. So all depends on geomechanical basic characteristics. This well geometry is also important for optimum completion design, right? Regardless, I mean, the cross section of the well and the trajectory of the well all are important parameters for completion design that needs to be basically optimized. And remember, we are dealing with high temperature formation. So thermal stress becomes an important factor. We typically ignore thermal stress, differential temperature and this type of, and the effect of, a temperature on plasticity of the rocks typically are ignored in oil and gas. In geothermal, we are not allowed to ignore those things. Thermal fracturing is also an issue, right? During drilling, we don't really want to initiate or reopen existing fractures, not to get losses, right? We don't want to lose the circulation, the fluid. And having high temperature, high differential temperature between formation and the drilling fluid basically make fracturing easier, right? So there's a very important factor to consider during drilling for geothermal. And for those who are not familiar actually with wellbore stability modeling, what we do, we basically develop a geomechanical model and then we calculate what we call it collapse gradient, right? Which is the minimum mud weight required to keep a formation stable. It means your mud weight should not go below collapse gradient to make sure no formation doesn't collapse. And then we calculate frag gradient is the maximum basically downhole pressure we can use without creating a fracture or reopening an existing fracture to basically initiate losses. And then we have pore pressure. Of course, we don't want to go below pore pressure not to get kicks and blowouts. So this type of wellbore stability models not only help us to basically optimize the mud weight, the drilling fluid pressure, but also help us to optimize the casing design, to optimize the trajectory of the well, and many other things that basically help us drill smoother. And one last comment I want to make here. So we are drilling crystalline rocks in deep geothermal systems, right? And although these formations like granites are more stable, but drilling granite is more challenging. So for this reason, industry is looking for new drilling technologies. And these new technologies need new geomechanical capabilities, right? I'm going to give you one example just to show you what I'm talking about. But the fact is that geomechanics should evolve as the industry evolves, right? Geomechanics need to advance and progress and gets better and better as new technologies coming to the market for geothermal. One example that I want to discuss here is millimeter wave drilling technology. You might have heard of this technology. It's developed by Quaise Energy, a US-based company. And is targeting basically super hot rocks, right? How to drill this type of rocks faster and more efficient. So basically we are targeting 10 to 20 kilometer depth reservoir, right? So this technology basically creates waves using a gyrotron and direct it toward the rock. And instead of drilling, it basically melt and vaporize the formation, right? So it's a totally new concept, totally new technology. And as you can imagine, the wellbore stability study and modeling for this drilling is totally different from typical oil and gas drilling techniques. We need to deal with melting the rock, right? We need to be able to see this melting effect on the near wellbore area, on what type of damages it applies to the formation, what type of instability issues it creates. So it definitely needs a different type of modeling, different type of parameters to be included in the model. Specifically, what I'm going to show here is the study that we performed with Quaise. We are looking at the stability of a rock of a well that has been drilled with millimeter wave drilling technique during production, when we are injecting and producing basically from the hot crystalline rock, right? So there is a component, a thermal expansion component acting here, plus a differential pressure due to basically injection or production, right? So this causes thermal degradation of the material. So basically, we are breaking the grains contacts, and again, this is not something that we look at when we drill with typical oil and gas bits. So what we did, we basically conduct extensive numerical modeling. Gabriel, do you still hear me? Because I see actually. Yeah. Okay. Sorry.
We can hear it.
Okay, so we did extensive numerical modeling using advanced, basically solutions with respect to stress calculation around the wellbore and characterizing the shear failure mechanism that is appropriate for these cases. And we were able to basically look at different scenarios for this case, and the result was that for this case, basically, there's no risk of wellbore stability issue during production, considering the injection strategies that we basically looked at. Just want to give you a flavor of how different basically geomechanics can be when we deal with different new technologies. So the second value that geomechanics bring to geothermal is with respect to induced seismicity risk. And I'm pretty sure you guys are familiar with the critical, how critical is not to create earthquake when you are operating subsurface, right? The reason is that induced seismicity risk involves human lives and capital loss, right? So is it showstopper really if we cannot manage it? And this is one of the reasons, like specifically in Europe, that most of you guys probably are sitting. Induced seismicity is a, showstopper, right? It's why fracking has been banned, right? It's why unconventional have never been developed in Europe. Risk of induced seismicity. So if we create this type of basically reactivation of microseismicity is basically coming from reactivation of the fault and fractures, right, which happen unintentionally, right? And this reactivation, this activity that happens on fractures and faults are basically coming from their geomechanical characteristics. How much stresses are acting on them, and how much strength these continuities have. Can they handle those normal and shear stress components on them or not? So if we reactivate a major fault, it can basically put the well integrity at risk, and also create caprock integrity issues, right? And these issues basically are huge loss to our wells and the reservoir. Now, caprock integrity basically can cause the failure of a whole field, right? So what we do in geomechanics, is basically looking at a stress condition around the major faults, major fractures, and make sure that injection doesn't change the stress field somehow that favor reactivation of fault and fractures that can potentially create microseismicity. The next topic is more on the reservoir performance side. At the end of the day, whatever we do, we want to produce. We want to harvest heat from the subsurface formation, and we need to maximize that just to be able to keep the project running, right, economically. So the importance is very high. Is not critical, because producing less or more, it just have impact on the capital and the benefit of the projects, but nothing basically related to human risk or other basically environmental risk. What we do here, the first thing is that we need to optimize the geothermal production system, right? Again, regardless what technology we use to produce geothermal energy, the system design must be optimized in order to maximize the heat extraction, okay? And majority of the parameters that goes into the system design is geomechanical properties. Again, how big are the stress components and the orientation of the stresses, and how mechanical basically properties of the formation get integrated and can support the project. So a lot of components basically going into system design are coming from subsurface characteristics. Remember, fluid flow, heat flow heavily depend on permeability and natural fracture system. So, and these two parameters are heavily dependent on a stress field. For this reason, we need to optimize the well layout, where to put the wells, the trajectory of the wells. Should they be vertical, deviated, or horizontal, or a combination? They all depend on the stress orientation, stress magnitude, and geomechanics, right? And we need to do that. We need to optimize the well layout and well design in order to maximize heat production. Injection strategy and also production strategy must be optimized. Again, we don't want to inject too high to create any induced seismicity, and it should not be too low to basically minimize the production, right? We need to optimize it. And again, it all depends on the natural fracture system and how we can get basically our operation involved with geomechanics of those fractures, permeability, porosity of the formation. So something that typically are ignored is that even if we do best evaluation of the of the fracture system initially, when we start producing, injecting, this fracture system start evolving, right? It's not an static system. So it changes. It means the stress around the fracture fault field will change, the pore pressure changes, and as a consequence, the mechanical behavior of this fracture changes, right? So some of the fractures start getting closed, not being conductive anymore. Some of them basically gets a little bit more permeable. So we need to be able to understand how the fracture system is evolving. Is it to favoring the production, or is basically against production? And hopefully be able to optimize the injection to manage this evolution and take it to the direction that benefits us, right? And it's doable with good geomechanical modeling and good understanding of the subsurface fractures. We can do that. And there are a lot of actually monitoring technology, advanced technologies that are coming to the market, which will help basically to calibrate and benchmark geomechanical models and keep improving the models to be able to do something like this. So if we deal with enhanced geothermal systems, so we need to stimulate the reservoir, what we call it in oil and gas, hydraulic fracturing. And people try not to use this term in geothermal word, but it's the same thing. So geomechanics become number one knowledge, right, to make enhanced geothermal system, and hydraulic fracturing successful. Hydraulic fracturing needs to be safe and optimized, right? And we need to understand the variation in stress field, variation in mechanical properties, the existence of natural fractures to be able to do that. Reservoir compaction is a typical, basically, process in oil and gas that we deplete the reservoirs, right? If we don't support the reservoir by injecting fluid, it will be depleted, right? And sometimes depletion actually helps to produce more, right? Because it's kind of a squeezing effect, like you want to get, toothpaste out of the tube, right? But remember, in geothermal, we are not producing fluid, we are producing heat. And it means that the system should be always, not depleted, right? We need to keep the pressure in the reservoir in order to be able to inject and produce, right? So one of the things that geomechanics can help with is to make sure that, we can keep control of the reservoir with respect to depletion and compaction. And just again, remind you that when we deal with geothermal, we need to add additional parameters into geomechanical models, things that we typically ignore in oil and gas. Temperature becomes very important. Differential temperature between drilling system and the formation, thermal expansion, thermal stress, heat conductivity, right? These are the things that we need to be able to include our geomechanical models. So I want to expand a little bit here on the role of fractures and faults, which basically determine the success and failure of geothermal projects. The role of this basically fracture system is to control fluid movement, right? With respect to the rate and direction. So we cannot really tell the fluid which direction to go. Near wellbore, probably we can, but as the fluid goes to the reservoir, it's natural fractures that define the orientation and the rate of the flow. And also temperature and anomalies, right? Fracture can act as conduits, right? Increasing permeability, which you all know, but it can be also act as barriers, right? Against fluid flow if those fractures are either impermeable because they are filled by like clay minerals, right? Or if they are geomechanically closed. And what does geomechanically closed means? I think in the next slide I'm going to explain to you what it means. So all depends on their orientation to the stress field. So if the fracture is conductive or non-conductive, it really depends how they're oriented toward the stress field. So, and here is the magic, right? A misconception typically among production engineers is that all the fractures are contributing into the production. It is not true, right? Right, because many of the fractures are basically not conductive because they're mechanically closed, right? Those fractures are conductive that are critically stressed or optimally oriented to the stress field. So just to quickly explain what I mean by that. So each fracture is under the in situ stress field, right? So if we translate this stress field into normal and shear components on top of each natural fractures or fault, and here I'm just showing it in two basically dimension, but it's a 3-dimension problem, so it's the same thing. So they will be translated to a normal stress condition and a shear stress condition, okay? And the ratio between shear and normal component of a stress should be higher than a specific value to enable basically activation of the fractures, which basically create shear movement, and shear movement create conductivity, create permeability. So fractures who are critically stressed, they are permeable. They can produce. They can let the fluid go through them, right? How we can find them? If we know the geometry of the fractures from image log or any other sources core, we can basically do a geomechanical analysis and using more circles, right? And basically shear failure criterion, and see which fractures are close to the shear condition or above. So these are the critically stressed fractures, and which ones are not active. So putting this information on a polar plot, we can see where are the productive cluster of fractures and where are the clusters that of fractures which are not productive, right? Like in this case, if you drill a vertical well, right, through this basically cluster of black or closed fractures, your production would be minimum, right? Or your injectivity would be minimum because you don't have enough access to productive, basically to conductive fractures. Now, if you drill a deviated well 60 degree toward, let's say, west here, this is how you can maximize your injectivity, your production. Okay, so it's not a magic. It's basically what science is, and we have been able to help oil and gas industry maximizing production using this concept. So now, learning from oil and gas mistakes. So geomechanics community, drilling community, and basically petroleum engineers, geologists have been doing several mistakes historically in oil and gas that prevent benefiting from geomechanics, right? To maximize that benefit from geomechanics. And I want to actually review some of them, and I believe we should not repeat these mistakes dealing with geothermal. Number one is minimizing data acquisition. So in oil and gas, it's always lack of enough capital to, or it's not lack of, people don't want to spend too much money on data acquisition. And at the end of the day, when there's no data, uncertainty in the model are higher. It increases the operational risk, and cost at the end will be several times more than the cost of acquisition. But in oil and gas, we have a space to take this risk because, again, the no benefit, the profit margins are quite high, right? In geothermal, we cannot. We really need to spend our money on to characterize the reservoir as much as best as we can, and then avoid this high capital cost here. Using two simplified models. So rocks are elastic, rocks are isotrope. There's no heterogeneity. Let's ignore fractures, right? These are the things that we typically do in oil and gas, and we should avoid that in geothermal, again, because the end result is losing a lot of money on the operational risk and non-productive time. So this is one example of very simple models. I'm talking about those numerical models as well, but here I just want to show you the wellbore stability models that typically in oil and gas people do, and it consists of a pore pressure and a very simple frag gradient model, right? And it has been proven that this model doesn't really help oil and gas and drillers. It might be actually opposite. It might be creating more problems. This model should be actually something like this, right? So where we have more details, more science-based, basically, frag gradient, and also collapse gradient becomes is a critical factor that typically people ignore. So talking about the same thing, stress dependency on lithology. So stresses change with rock properties, with lithology. We cannot just make them a simple curve or simple line and say this is the stress model. It is a mistake, right? Ignoring collapse gradient, as I already mentioned. So most of the what we call the PPFG models, they ignore collapse gradient. So this is a quick comparison between a PPFG model and a geomechanical based wellbore stability model. And you see that, if we follow the recommendation from this model, we will basically lose the well, right? You see how mud weight window is narrower actually than what we predicted by ignoring, collapse gradient. Fracture pressure is the same as minimum horizontal stress. It is by far the biggest mistake that is still a lot of people out there are making, right? Minimum horizontal stress is a far field stress parameter, right? It doesn't get affected by our operations, by drilling specifically, right? While frag gradient, frag pressure is a near wellbore phenomena, right? Is affected by well trajectory, by drilling exercise, by mud weight, right? But by mud composition. So we don't really need to limit drillers to the minimum horizontal stress at as their upper bound for drilling fluid. Okay, so I'm just showing you here one example of us going from minimum horizontal stress to frag pressure as the upper bound of the drilling window, and you see that in this case we could eliminate actually 2 casing shoes, right? 2 casing string, by just not assuming that minimum stress is frag gradient. And people who are in drilling business, they know how much money you save if you remove 1 casing string. So ignoring anisotropy, a big mistake, right? Anisotropy have extensive effect, important effect on stability of the wells, on reservoir performance, on hydraulic fracturing, right? And in many cases, we just ignore them because either we cannot characterize them or we just think they're not important. And ignoring natural fractures. We talked about it and you all know how important natural fractures are. And the last thing, in the reservoir engineering realm, people basically define a relationship between porosity and permeability, right? Either in the ambient condition in the lab or even under a stress condition, a constant stress condition in the lab. And they create a relationship and then apply this relationship everywhere in the reservoir, right? But the thing is that this relationship is depth dependent, right? As you go deeper and deeper, this relationship changes, right? Because the changes of permeability and porosity with depth is very different, right? Permeability is typically much more sensitive to depth than porosity. So is a big mistake basically in calculating the reserve, in calculating the productivity of a reservoir, if we just create this under a specific stress condition and apply it to any stress condition, right? So these are basically to me, the major geomechanically related mistakes that we have been historically doing in oil and gas, and we should avoid going toward geothermal. So this section, I quickly talk about the role of technology development, because there are several gaps in geomechanics that needs to be filled, specifically if moving to more advanced applications like carbon storage, like geothermal. And I would like to actually start with quickly reviewing the dependency of geomechanical models to logs, right? What we do, we develop a rock property models using several different logs, right? Including dipole sonic density and so on. And then we expand this using these mechanical properties. We basically can calculate in situ stresses, predict pore pressure using several methodologies that we have and they have been around for many decades. I don't see too much improvement actually in these models that we typically use. And then we converted to wellbore stability model that can be used for drilling and also hydraulic fracturing. So the question here is that, or the concern here is that geomechanics is heavily dependent on logs. One of my biggest challenges working in the industry for 25 years only doing geomechanics is lack of data. Logs are not always available, specifically logs that we need for geomechanics, dipole sonic, density. And this limits geomechanics quite a lot. There are a lot of cases that we cannot really do anything about it because we don't have the logs that we need. Even if we have the best suit of logs is only in the pay zone, in the reservoir. How about the overburden, right? Don't we need to drill overburden to get to the reservoir? Of course, we need geomechanics for overburden. There's no logs typically in horizontal sections because wire line cannot be run, right? So there are a lot of limitations coming from these logs, right? So what we did, I'm just giving you an example from Tavera, how we dealt with it, and we came up with a new technology called DDG, Drilling Dynamics Geomechanics. We found that, there are actually a lot of geomechanical information hidden in drill bit vibration data. And this drill bit vibration is the data coming from, basically, you need to put a little sensor close to the bit to measure vibration. And also, the drilling parameters, the typical drilling parameters that everybody measures while drilling, these data, if are processed properly and filtered, processed, and then using machine learning, translate them to geomechanical properties, we can extract almost all the geomechanical properties from this data without using any logs. Okay, so we developed this technology. We tested it in like 8 different onshore and offshore fields, also geothermal, like Utah Forge. And the technology is working, it's very efficient, and we are commercially using it right now just to address this gap, right? Dependency on logs. Why should we stick to logs for many decades while we know logs are not sufficient typically? So it creates actually a real-time opportunity for geomechanics. It creates opportunity to optimize frac design in basically for shale gas, for enhanced geothermal systems, and a lot of other basically advantages, cost saving on logging, right? We don't have to push our clients to go and run dipole sonic if they don't really need it for other applications. So I just move faster on this one. I think I explained this. The second challenge that I believe is my top basically challenge in geomechanics is calibrating a stress model, right? When we develop rock property models, typically we have some rock mechanics lab testing result that we can calibrate it with. Pore pressure, we have some well testing that we can calibrate the pore pressure model with. For stress calibration, we absolutely have nothing, right? Except a mini frac or extended lick-off test that can, one of the stress component can be interpreted from it, right? And there's not enough. So the biggest uncertainty in geomechanical model to me is a stress model because we cannot calibrate it, right? So we really need a tool that we can put it downhole and measure stresses and measure directly, not indirectly. There are some technologies that measure deformation and they back calculate the stresses. They're very uncertain. Fracking is uncertain because, again, we have to interpret the decline curve. So what we did at Tavera, we came up with a very smart, basically, direct measurement technology. Unfortunately, I cannot show the design of the tool, but the tool can basically characterize full stress condition around near wellbore in a depth. And it can move to different depths and repeat these measurements and give you the actual stress around the wellbore, right? It is not interpreted or estimated. Unfortunately, most of the effort in the industry as of today has been on estimation, just bringing better estimation methodologies for stress, not measurement. It is very critical to have a tool to be able to do the measurements. And another product that we develop is Geodeck, is the visualization tool that basically, something that I was not happy with using different commercial software was visualization and having enough sufficient analytical tool to basically understand the model, compare different scenarios, different models. So again, we developed this product called Geodeck. It's not a geomechanical software, but it's a visualizer. You can basically put your model into this visualizer and have a lot of tools to basically do analytics, to create 3D visualization, 1D, 2D, and so on. So Gabriel, if I'm out of time, I can skip this section and answer the questions. I think I'm out of time, right?
Well, I mean, we're never out of time, right? So if you can keep going for another 5-10 minutes, and then we can.
I think I have 5 minutes maximum here.
Okay.
To
All
finish
right.
this. Yeah.
Perfect.
Okay. Yeah. Again, this based on learnings from oil and gas, based on what I have done in the last 25 years in geomechanics space. The next few slides, I just want to show you the trends of geomechanics, where geomechanics is going right now and in future to basically better serve new applications like geothermal. And again, is my understanding, right? Yours might be different, or other people might have different opinion. It's starting with actually geomechanical modeling. So far, I mean, initially, like we have been really focused on static geomechanical models, either based on log or based on seismic data, right? And using this data, we can basically calculate the rock properties, stresses, but this model are static. It means they are not connected to any engine to basically look at changes in the subsurface and see what happens to the geomechanical model, right? They're high uncertainty, again, because of the high uncertainty in the data, and low resolution. Like seismic, we know seismic is not a high resolution data. So the models are really low resolution. So historically, we started actually moving to more dynamics models with numerical modeling, right? These models can be coupled with reservoir. You will see when the pore pressure changes in the reservoir, the reaction of the rocks will be actually reflected to the geomechanical model and vice versa. It means whatever, if you change any parameters at any point in the model, you will see the effect everywhere else, right? The only challenge of this basic numerical modeling is still low resolution, because we cannot really increase the resolution because of the computational limitation, and also, again, the source of the data that are imported to these models. The future trend is more, or it has been already started, actually, is nothing, I can call it new, but for geothermal, we really need to go for thermo-hydromechanical modeling with more powerful software, right? With more computational capability that the industry is moving toward. There are a lot of computational power improvement recently in national labs, in commercial basic products. We can do a lot more, like working on the edge, working on the cloud, for example, right? So the new generation of software should be web-based, should be connected to data bases now on clouds. So we can work with higher resolution model. We can increase the accuracy of the model, and we can couple different things. We can couple geology to reservoir, to geomechanics, and include a lot of more complex parameters, right? To continue on the modeling, historically, most of our model has been using continuum mechanics, right, to do geomechanical model. Then we started actually looking at discrete element modeling, because we found that fractures, faults are really important, right? And this type of model sometimes can, but sometimes basically falls short in modeling, discontinuity. And the future that has been started again already is grain scale modeling, right? If we really want to be able to accurately predict subsurface, we need to model grains, and how the grains are connected, how fractures are basically developed among these grains. So we have software that basically can model grain base, but in small scale projects. I'm not aware of any capability right now, again, because of the computational limitations to be able to do this type of modeling in a larger scale, like a field scale modeling. Okay. So historically, we have been doing geomechanics on our desktop, right? Again, using data, typically post-mortem, when the modeling, when the drilling has been done, we just use the data and we try to predict the future well, right? By very simple assumption, going from one well that we have a geomechanical model to a planned well where we only know the formation tops, right? So the direction is basically going to quicker numerical modeling. We have reduced order modeling technology right now that we use. We take advantage of, artificial intelligence to increase basically reduce the time of, numerical computations, do real-time analysis and real-time risk assessment, risk evaluation. We are moving toward virtual reality, augmented reality to basically entertain collaborative work on geomechanical modeling is very critical. And having decision makers with us is very important to have access to some sort of facilities to be able to openly talk, technical people talking to decision makers and vice versa, and make quick decisions, right? Talking about the experimental work, you're all familiar with triaxial cells, right? To basically simulate the subsurface condition and calculate rock mechanical properties. We all know that triaxial is not true triaxial because we cannot simulate the horizontal stress, in isotropy. So we already started using what we call it true triaxial cells or polyaxial cells. For geothermal, we definitely need to add high temperature capability to this. So I'm aware of many of these equipments in research center, even in some commercial companies, but I'm not aware of any high temperature, basically polyaxial facilities. Maybe I'm wrong. And again, characterizing rock mechanical properties, we are heavily dependent on labs right now. We have to take core, take samples, take it to the lab, which is a very lengthy, basically, process and very expensive. The future of measurements is field measurement. We need to basically take all the measurements to the field using different concepts like scratching, for example, of the wellbore wall to characterize the mechanical property. It's just an idea, but there are a lot of things that we can do in situ in the bottom hole or in the field to basically do this characterization, because one of the biggest challenges right now is to upscale this mechanical measurement in the lab to the field. And there are a lot of questions about what typically was the best industry practice right now in geomechanics. Okay, so with that, I quickly summarize and leave some time for questions. So first of all, geomechanics play a critical role, right, in identifying risk, mitigating risk, and helping to optimize the design for any type of subsurface projects, right? Geothermal, oil and gas, carbon storage, energy storage, from drilling, from even exploration phase to drilling, to fracking, to production, completions, everything needs geomechanics knowledge, geomechanical modeling. It's more pronounced in geothermal because geothermal systems are more complex, right? They're more complex. There are lower profit margins in geothermal that increase the dependency on basically reliable geomechanical models. And as I mentioned, drilling and production technologies are improving for geothermal. So geomechanics should also advance and catch up with this. So it's very important. Need for more realistic measurements and modeling. There are a lot of uncertainties coming from input data, coming from lack of calibration data, coming from tests that have been done in the lab, not in the field. These are the things that opens a lot of basically research and development opportunities for geomechanics community to improve and provide the needs of, to address the needs of geothermal energy. And my last comment, which I typically do at the end of all my presentation, geomechanics is very complex, is not a simple discipline, right? It needs a strong understanding of mechanical engineering, of the mechanics of the earth, plus geology. Please do not do it if you are not ready for it. If you don't have the right background, if you have not received like at least 1 year on-job training, being mentored by an experienced geomechanics person, never sit by your computer and do geomechanics and deliver to your client, right? Because geomechanics can be, as much as it is helpful and can save a lot of money and risk, basically mitigation, it can be as dangerous and put you in trouble and create more trouble. To me, not having a geomechanical model is much, much, much better than having a wrong geomechanical model. So that's my last message. If you want to be a geomechanicist, you have to actually have a strong background, engineering, geology background, and a lot of experience. Thank you very much for your time. And I'm ready to answer any questions. And I put my email here as well if you have any question later, if we go out of time. So let me turn on my camera. Okay.
Thank you very much, Dr. Soros, for this very interesting presentation. You touched on a lot of important points. I think this last one really stuck because I'm sure half of the audience, if not more, is aware of what happens when you inject fluid downhole. You don't understand the dynamics, and now you suddenly have induced seismicity, and now you have loss of lives, loss of support from the communities, loss of support from the government, and now you find yourself 10 years behind with development of geothermal energy. So I really resonated a lot with your last comment there. I think it's super important to be aware of the capabilities and what we're doing. As a matter of fact, I looked up the Pohang project, and the first title that came is, lessons learned. And
yeah.
I think we should try to avoid making the same mistakes we've done in the past, especially with such an abundant clean energy source that's available. We need to do our best to leave it to those that understand the subsurface. With that comment, I'm gonna move into the questions real fast. We have a question from Thomas Franson that asked, "What kind of quotes evolution do you expect on fracture systems?"
Sorry, what was the question again? I didn't catch it.
What kind of quotes evolution do you expect on fracture systems?
Oh, what type of evolution? Okay, so I think I refer back to the slide that I talked about critically stressed fractures. So we keep changing the stress condition subsurface by injection, by production, right? By hydraulic fracturing. Almost whatever we do, we are changing artificially the subsurface condition. And that stress condition change will change the characteristics of the fractures, going from a non-conductive fracture to being conductive or vice versa, and even some sort of changes in the direction of the fractures, right? If they get activated, I mean, their size expand, their orientation changes, and all these things together will change the production, right? And we want to be able to understand that changes, that evolution, and be able to react to it, to guide it toward the orientation that we need, right? Yeah, I don't know if I answered the question properly, but it's more mechanical changes of the natural fracture system.
Basically a dynamic system, a dynamic monitoring of what's changing downhole. Perfect.
Exactly.
He had another question that it started with, and he said, "Is thermal stress the biggest stress factor, or rather stress caused by the huge production rates, especially from fractured zones?"
Yeah, that is a good question. The quick answer is no. Thermal stress is not as big as, compared to the magnitude of the stresses in deep project is not a huge component, but it has important effect, right? It has, we should include that, like in summary, we should not ignore it.
Okay, perfect, thank you. There is an additional question from Chris Hopstack, and then there's a very interesting tool you talked about, about the stress measurement, and he said, how do the costs compare to, a regular mini microfrac test, and why is, DFISS giving more accurate results in your opinion?
Yes, cost-wise, it is. We believe that 30% of the cost of conducting mini frac, and time-wise, the whole measurement in one depth is less than 1 hour, right? So we save a lot on the time as well. The advantage is that it gives you all the 3 principal stresses and is not interpretation. It is direct measurement. So that's the big things that we claim is the direct measurements, right?
But that is huge, right? So that's one of the big things that we need to know. My question would be, what is the temperature limit on that? If you
Yes,
have
so the current tool that we are prototyping right now, it targets the oil and gas application. I think the highest temperature is 300 Fahrenheit. Someone should translate it to Celsius, but then we will upgrade it to 450 for geothermal, right? That because we started, I mean, we decided to start with the lower temperature and then do some experiment and improve it.
We definitely need an advancement on that if we want to develop those, you know,
Yes.
hot rock
If you have money,
situations.
Gabriel, bring it on.
All
Put it
right,
on the
I'll
table.
make that work. All right, so we got a bunch of questions coming in from Robert S. It says most of your concerns are valid in drilling and EGS production. What about geomechanics concern during AGS closed loop production?
Yeah, so again, I go back to the drilling complexity of AGS, right? I mean, how wellbore stability, how trajectory optimization with respect to the stress orientation needs to be optimized, right? So remember, we are spending quite a lot of money on drilling on those technologies. And if we just select a wrong orientation, imagine all the drilling goes well, but the system, the radiator is toward the wrong orientation. You will not get the production that you expect, right? So as easy as that, right? And reservoir aspects, I don't see a lot of, because we are not dealing with induced seismicity, so there are less reservoir geomechanics related aspects to it, I would say.
Okay, thank you. The next question is from Joshi. It says, how to get more information from drilling parameters that you explained? Do we need real-time data or DDR also work?
So, so what we call it drilling dynamics data consists of, drill bit vibration, which is a very rich, high resolution, high scanning rate data, and then drilling parameters, which are lower resolution. Each of them carry information about subsurface, bit rock interaction. That's the word, right? So the art is to be able to, because this data are also dependent on many other parameters, like the drilling system configuration, bit type, size of the bit, right? Plus bit rock interaction, right? So the key here is to be able to process the data, get rid of all those noises, what we call it noise, but in drilling, they use those noises for drilling optimization. And make sure that we use the frequency of the data, which is related to bit rock interaction and subsurface condition, right? So data are very rich, methodology becomes very important, and artificial intelligence basically help us quite a lot to be able to work with this data.
Okay, thank you. We have a comment and a question from Pejman Shoaib. Excellent presentation. In the future trends, it was mentioned the importance of THM modeling. I was wondering what not THMC, also including chemistry, especially for geothermal systems with scaling issues and the new trends of mineral recovery, which will potentially change formation to rock structure around injection wells. Any insights on this?
Yeah, so it's absolutely because of my lack of knowledge about chemistry. So it doesn't remove the importance of chemistry. I could not really talk about that. Yeah, but you're absolutely right, Pejman. Chemistry is very important in geothermal and it should be included. Yeah.
Especially now that we're maximizing the use of geothermal brines and trying to, basically make the most out of it. Great question. Maybe something we will look into doing an event on actually the geochemistry in terms of geothermal reservoirs. I think that's important.
By the way, Gabriel, there are studies actually done by national labs and some companies like operators to combine chemistry to geomechanics. And there are papers out there. I didn't talk about it again because my knowledge is very limited in that area. So
we will target this. All right. So we have a question from Soraya. She said, hello, Hamid. Are there a lot of concerns related to the evolution of permeability and porosity due to geochemical reactions? Yes.
Yeah, in geothermal system is one of the scaling chemical reactions and closing the pore space, losing permeability is a major concern. And I think there are many researchers, universities are working on this topic to basically minimize this effect by using optimum fluid composition or other methodologies. Again, it's not my area yet.
Okay. From Tai Subia, the question is, are you able to visualize shallow groundwater aquifers in a geomechanical model? So data for monitoring groundwater. I suppose maybe with
Yes.
Geotech, I think that was the whole question.
Yes. With Geodeck, basically, we can visualize any type of data from raw, raw like geophysical data, seismic data, all the way to model data and monitoring data, right? There's a wide range of basically input that can go to Geodeck. Yeah.
Perfect. Thomas Franson thanked us for the interesting presentation. Robert Estes made a comment. He said, "Nice presentation. Thank you. It is ironic. It is ironic that you urge obtaining more data measurements during geothermal well development than petroleum when geothermal tries to minimize cost of drilling."
Yeah, and Gabriel, is very important because people think that because the investment on geothermal is less profitable, we should minimize data acquisition. Is the big mistake, right? So because again, the cost at the end because of not having good model is several times more than data acquisition.
And I think where we fail, and I hope the audience gets a glimpse of this, I think where we fail is when we ask for data in the technical world, sometimes we'll fail to convey the value of that in terms of those that hold the budget, right? What do you do with that data? What do you do with a stress measurement? How does that affect the model? How is that going to avoid induced seismicity and basically a catastrophe, right? These have been the reasons why we haven't really moved forward with certain projects. And I urge those that are in Europe, you know, I know that fracturing has been a little bit of a topic, let's say, but in the United States, this is being done. So with proper tools in place and the right people in place, this can be planned for, and we can try to harness a lot more heat than we're actually doing in the present. At least that would be my insight on this.
And there's a language barrier between technical people and decision makers, typically, right? Is what I faced in geomechanics community, at least. It's hard for technical people to communicate values to decision makers because decision maker doesn't care how good my stress model is. They care about the value, what
Exactly.
dollar they save, right? If the stress model is better.
Next thing I'll find myself doing is using ChatGPT to make the message clearer and get it across. But
Exactly.
I would like to thank you for your time. And thank you for this actually very insightful presentation. There's a couple of things that popped up here that are super interesting for projects. And hopefully we connect later on this. What I'd like the audience to know is that we will be sending a sanitized version of the slide deck in PDF format. And we will also be sending you the link to the recording. I think it would be great if you follow us on LinkedIn in terms of our pages, the different sections, and let me know if you have any questions. What we will do is we will be doing a session in February, and this one will be focused on basically the modeling part of the geothermal reservoirs. And as a matter of fact, now that we talked to Dr. Hamed and we got so many questions, most probably March or April, we will dive into geochemistry and how this affects the whole world of geothermal, right? So if anyone has ideas and would like to be part of this, please get a hold of me, a hold of us, and we can, make things work. Thank you all for being here today. Thank you, Dr. Hamed, once more. And we will stay in touch. Thank you.
Thank you, Gabriel, for the opportunity, and thanks everyone for bearing with me for more than 1 hour. Thank you very much. Yeah.